Welcome to Texas State University's Organic Chemistry 2342, Organic Chemistry 2. I'm your guide, Dr. David Urban, and we're going to begin with Chapter 13, Conjugated Unsaturated Systems. Okay, so one of the things about the conjugated unsaturated systems is they have different reactivity than our standard double bonds that we had in a previous chapter. So what do we mean by conjugated and non-conjugated systems? And the first thing we have to have in a conjugated system like that is to have a double bond. But then we also have what we call polyenes. Polyenes are compounds that contain more than one double bond. And so if it has two, it's a diene. If it has three, it's a triene, et cetera, et cetera. Okay. So when we're naming these polyenes, we need to start first with the parent hydrocarbon chain. But in this case, the longest chain that contains all of the carbons with double bonds. Okay, so after we figure out the longest chain with all the double bonds into it, we need to figure out how many double bonds we have and identify it as either a diene or a triene. Then, of course, we want to do our numbering system where we have the lowest number possible at the first double bond, and second and third, etc. And then we also have to add our E and Z where appropriate. To remember your E and Z nomenclature, please review Chapter 7. Okay, so for example, we have an unusual one here to start with first. This is called a culminated double bond because we have two double bonds on the same carbon. Okay, and so this simple little molecule is going to be the 1,2-propadiene right here. One of the more common systems we have is our nice little 4-carbon chain here called butadiene, and it's 1 for the first carbon of the double bond, and it's 3 for the first carbon of the second double bond. Now, of course, when we go into cis and trans and E and Z, we need to identify those correctly based on those rules. One of the interesting things is that a triple bond will also change the name of our polyene system. And whenever we have a double bond and a triple bond in the same compound, we call that an ene-ine. And of course, we identify the alkene first and then the alkyne wherever it appears in our molecule. And we can extend these rules to many different systems, including cyclic systems or longer chains. Okay, so as I said before, we had different types of dienes. The first one we had was that culminated diene where we have two double bonds on the same carbon. But we also have two other types of dienes. And the two other types of dienes are what we call an isolated diene. And that's where our pi bonds are far enough apart that they cannot electronically see each other. What this means is that there is an sp3 hybridized carbon in between the double bonds so that they cannot have their p orbitals overlap. The other type of diene we have is what we call a conjugated diene. And so we have an alternating double bond, single bond, double bond, where we can have partial overlap of our pi bonds, our p orbitals and our pi bonds across that sigma bond. Okay, so let's take a little bit deeper look into that conjugation concept here. So in the conjugation, in our conjugation, we have to have overlap of p orbitals. And when we look at our pi bond exists because our carbon is sp2 hybridized and we have a remaining unhybridized p orbital. Now, in the case of a single double bond, we have a single electron in each of those p orbitals, and they share above and below the sigma to give us our first double bond. Okay, when we have only a single sigma bond separating them, we now can have the overlap of the first double bond with the p's of the second double bond if they are coplanar. Notice that all of these can blend together now because they can all overlap to give us this pi cloud above and below. Okay, so this can happen if we have 3 or more p orbitals available to us, and when we do, we can delocalize those electrons over those p orbitals. So let's talk about that in a little more detail. And starting with just 3 orbitals, we can have what we have like this. This is called an allylic carbocation. Okay, so we have a double bond that has our normal number of electrons in it, our pi bond, and then we have an sp2 hybridized carbocation. Remember that our sp2 hybridized carbocation is a trigonal planar structure with an empty p orbital. giving it its positive charge. So in the case of this, when we have our carbocation in conjugation with a double bond, we can spread those 2 electrons across 3 orbitals, giving us our hybridized or our delocalized carbocation. So if we look at our resonance structures possible, we can actually have our carbocation on one side of the bond, or by just flipping electrons over, it'll end up on the other side of the system. So if we have only hydrogen in the system, it's called the allele cation. And if we have substitutions, we call that the allylic cation. Okay. And again, it's stabilizing those, it's having those 2 electrons spread across all 3 orbitals, stabilizing that lack of 1 electron, that positive charge. Okay, so when we look at this allylic cation, we have to think about its resonance structures. One resonance structure would be with the double bond only on one side and the positive charge, and then we can move both electrons to the other side, giving us our positive charge moving back and forth. Remember, when we have resonance, either one of these 2 extremes is not really how it exists. It actually exists more as that hybrid in between the 2. And that's where we have these partial double bonds in between the carbons here and a partially positive charge at each end, okay? So all allylic cations have those 2 hybrid forms, and is the hybrid of those 2 resonance forms. The positive charge is delocalized over the 2 carbons, meaning that's where the reactions are going to happen if you're attacking with a nucleophile, okay? Just like in the carbocation stability range, we have additional stability for the more substituted the allylic cation is. And because of this delocalization, that substituted allylic cation is actually more stable than a tertiary carbocation because we have a conjugated tertiary carbocation. So in the case here, we have substitutions, which gives us our conjugated tertiary carbocation. And then our next most stable is our tertiary carbocation, as we learned before. And then our allylic cation, because we're sharing that partial primary charge over 2 carbons, it's a little more stable than even our secondary. And then of course, our primary and vinyl cations are our least stable of our carbocations available. So when we talk about conjugation, we actually have different types of conjugation. And I'm sorry, different types of resonance. And so I want to go into the 4 different types of resonance we see. And in this chapter, we're looking at these conjugated double bonds, where we have alternating double bond, single bond, double bond. So that's one type of resonance structure we can have. And we see that resonance structure available to us in benzene, where we have alternating single and double bonds. We also see that in things like butadiene and the charged species like the allylic, other polyenes. Okay, so if we look at the resonance structure for butadiene here, we can have the electrons move back and forth, giving us a separated charge of plus and minus, and then can flip back to give us our stabilized uncharged species. Okay. The other type of resonance we can have is where we have pi bond adjacent to another species that is either charged or has a radical. So for example, if we have a double bond next to a species that can either be a cation, it can be an anion, it can be a radical, or it can have a lone pair. In any of those situations, you can have the electrons move back and forth without breaking any bonds. And so you would be moving that charge, moving that radical, or moving that lone pair back and forth across the system, giving it stability. The third type of resonance we have is what we see in things like charged species, where the overall charge of where a positive charge can be stabilized by an adjacent lone pair. So where we can have the lone pair come in, form a temporary double bond, and moving the positive charge over to another species. So this takes place in something like ether right here. If you have a positive charge on next to an electronegative atom with a lone pair in it, it can actually go and stabilize the one charge and have the charge reside on a single atom. So this is another type 3 of our resonance possibilities. The fourth type is what we see in carbonyl compounds.
where we have a difference in electronegativity between two atoms in a double bond, allowing us to have charge separation or partial charge separation. Okay, so just like in the case of our ketones from our last chapter, we know that, but by resonance, we can actually separate that charge into two different species, giving us our partially positive carbon and our partially negative species, oxygen. Okay, so those are our different types of resonance. Let's remember our rules for resonance that we started with in chapter 2, and we're going to add a couple to it. First and foremost is the resonance structures, either extreme, is just to give us an idea of where the electrons might be. The resonance hybrid is real, okay? So the resonance hybrid is what gives us, our reactivity and our reactions. The second rule of resonance is only electrons move, never atoms. You never move a hydrogen, you never break a bond. All you do is move electrons back and forth, back and forth. Okay. All resonance structures must have proper Lewis structures, i.e. you cannot have more bonds than you can have. So for example, you can only have 4 bonds to carbon. You should only have a couple bonds to each of the other, a single bond to hydrogen, etc. Okay. All resonance structures must have the same number of unpaired electrons, meaning if you had a single radical in your structure, you need to only have a single radical in each of the resonance structures you have. If you have a delocalized pi system, those p orbitals must be coplanar. Remember our picture up here, all of these have to be coplanar. If they are not coplanar, they cannot overlap. If they're tilted away from each other alternately, like 90 degrees out of plane, they cannot overlap, therefore they will not work. Okay, so the 6th rule is the energy of the resonance hybrid is lower than the energy of any of the resonance contributors. And that's because having less of a delocalized charge, having it blended across multiple atoms makes it more stable. Okay, and the more stable resonance contributor is the one that contributes more to the resonance hybrid. So in the case here, we have a delocalization across 2 possible carbons here. In structure number 6 here, we have a tertiary carbocation, and structure number 7, we have a primary carbocation, which means that more of 6 is contributing to a resonance structure than 7 is. But again, our hybrid structure is here, but we know that there's going to be more positive charge on this B carbon because 6 is a major contributor. Okay, so let's talk about the stability of our resonance contributors. Okay, so there are 3 rules with stability for a resonance contributor. The more covalent bonds a structure has, the more stable it is. So for example, here in this structure, we have a total of 1, 2, 3, 4, 5 covalent bonds. In here, we only have 4, and in here we have 4 because of that charge separation. Okay, so structure 8 is a more stable resonance contributor because it has a total of 5 covalent bonds instead of just the 4 covalent bonds seen in structure 9 or 10. Okay, the other thing is that charge separation decreases stability. If you have a positive and negative charge on the same compound, why not just find a way to have the electrons contributed so you have no charge on the system? So if you have resonance contributors that are plus, that have a charge separation, and one that has no charge separation, the one with no charge separation is always more stable. Okay, and contributors that have an incomplete octet are especially unstable. Okay, so for example, in the case of this structure here, carbon only has 6 electrons in it when it has that positive charge on it, so that it would be less stable than if we were to move that charge over to the oxygen. Notice this carbon now has 8 electrons on it, and the oxygen also still has 8 electrons on it. That makes it more stable. So let's look at this last one here. So in this possible resonance contributor here, we have a charge separation, but we also have an incomplete octet on there on that oxygen. Okay, in this resonance contributor, we have charge separation, which also decreases stability, and we have an incomplete octet on the carbon. Okay, so just by kicking these electrons in here and kicking these electrons out here, we're going to get to our major resonance contributor, the one without charge separation, the one with more covalent bonds, and the one with a complete octet on each of the atoms. That concludes our Chapter 13, Part 1, Conjugated Unsaturated Systems.